just look at the form of the solutions we found for the harmonic oscillator, because the symbols can be kind of off-putting. And then we're going to do a couple of voting questions on these. You know, it's important to keep in mind that all this garbage out in front is just a normalization constant, okay? But these Hermite polynomials and a Gaussian function, it's not too bad, right? I mean, this is these are all polynomial functions. They're even, then odd, then even, then odd, and so on. And they're written in terms of this kind of off-putting symbol, xi, but that's proportional to x. So it's just trying to take as many of the extraneous variables out of there as possible. Xi is kind of like x. So just to test your intuition on this kind of expression and how it behaves, in particular, as x goes off to plus infinity, what's the behavior of those functions hn of x as x gets really large? What do they do? Okay, let's see a vote. Yeah, I'm seeing all ones or A's, and that's the correct answer here. They're polynomials, right? Polynomials as a function of xi or x. And you know polynomials, they're like linear functions that go to plus or minus infinity, or quadratic functions that always go up to plus or minus infinity as you go off to plus or minus infinity, or cubic functions and stuff like that. So all polynomials diverge if you go either to plus or minus infinity, which seems a little bit worrisome because this factor gets big. But what can you say about the behavior of any power function put next to a Gaussian function as x goes to infinity?
I can't see the presentation.
Oh, I'm sorry. Thank you, Elvis. I forgot to share it. Let's see. Share screen.
There we go. Thank you.
Thanks.
Let's see.
Okay, so we've got a power function x to the m next to a Gaussian function as x goes to infinity. We'll assume that constant a is positive. Both constants a are positive for the sake of argument. Let's see a vote here. Yeah, I'm seeing a lot of 4s so far, and I agree. Psi goes to 0. You may have heard, even though we got a product of something going to infinity, so this is a component of a polynomial, so it behaves kind of like it is a polynomial by itself, but it behaves like polynomials. It goes off to infinity. But this one goes to 0, and this one goes to 0 so rapidly that the product still goes to 0, even though one of the factors is going to infinity. You probably heard about that in your math classes, and maybe you talked about it in the context of limits or something like that. And it goes to 0 so fast so as to make this normalizable. Of course, we would have had a big discussion about how it's not normalizable had that ended up being the case. But this is a perfectly normalizable wave function. When we take the magnitude squared of it, the product goes to 0 fast enough that there's a finite area under the curve there. And so again, just going back here are our wave functions for n equals 0 through 3, 0 through 4, 0, 1, 2, 3, 0 through 3. And here are the corresponding probability densities over on the right-hand side. And you can see that the probability density looks like it's falling off rapidly to 0 So it certainly appears that there's a finite area under the curve. You can't really tell with your eye, but that's what we're seeing there. In the classically forbidden region, it very quickly goes to 0. Questions on either of those two? Voting questions, or I'm just making a couple of last comments. Here's something I made a comment about last time, but there's a discussion of it just at the end of the harmonic oscillator section. And that is, we talked about the form of the time-independent Schrodinger equation in the case where we imagine, well, let's just look at a very tiny region of x. So v of x is approximately constant. If I just take a little tiny area of the x-axis, v of x doesn't change that much. And so this thing inside the big parentheses here is approximately a constant. And we already said that in order for there to be a normalizable state, E has to be bigger than the minimum of V. And therefore, the thing in the small parentheses is positive. And so the thing in the big parentheses is positive. It's got a minus sign out in front of it. And so generically, in that small region, how is the solution going to behave? Well, if in the case where if you're in a region where E is bigger than V of x, in other words, the energy of your state, you're in a region of the x-axis where V of x is rather small, it goes underneath your energy of your state, then the thing in the big parentheses is positive, and you have the second derivative with respect to that. I guess I'm connecting back to the way you might have written it back in ordinary differential equations, but in our context, this would be d squared psi dx squared equals minus omega squared times psi back again. But here it is for x as a function of t. You get oscillatory behavior, linear combination of cosines and sines, right? When you take those two derivatives of those functions, you get an omega squared and a minus sign back again. Whereas if this thing in parentheses is negative, with the extra negative outside, the constant out in front of this psi becomes positive. And in those regions, we have what's like exponential growth and decay. And so, you know, I don't know if I have this forward here. Yeah, well, so probably flipping back here is best. Here's the energies, right? E equals 1/2 h bar omega, shown as this line, 3/2 h bar omega there, and so on. And you can see in the regions where the energy is bigger than the potential energy, energy of the single energy state is bigger than the potential energy, it's oscillating. And then once it gets less into a region where it's less, it decays away very quickly. It's not exactly exponential decay because it would be exponential decay if the potential were constant out there, but our potential is changing. So it's some other kind of dependence that still falls away rather quickly as you go off to plus or minus infinity. And of course, this isn't exactly cosines or sines. As you can see, the amplitude's changing, and that's because the potential energy is not exactly constant in there. It's changing. Okay. So that's true in general, not just for the harmonic oscillator. If you're in a region, maybe I should draw a picture on the board. If you're in a region where the energy of the state you're concerned with is bigger than the potential energy. So if I plot v of x as a function of x, and you have, you know, some potential energy function that looks like this, and you're concerned, you've solved for a bunch of different energy eigenstates, and this is En, which corresponds to a state psi n as a function of x. Here's a region where En is bigger than the potential energy. And what we kind of know is that in that region, the wave function is going to, so, you know, psi n, not the wave function, but the TISE solution is going to oscillate in that region. And then once I get out of there, it's going to decay away very rapidly. Same thing over here. You know, it might overshoot and then decay back away. So you can kind of get an idea of what those psi n's should look like. There's one more bump every time you go up an n. You know where it should oscillate, and you know where it should be exponential growth or decay. All right. That's the end of the harmonic oscillator kind of stuff. And now we're on to the next section. Any questions before we move on? Which sounds super boring, but there's a lot of interesting mathematics in it that maybe you've seen in other courses or maybe you haven't. So what I'm saying here at the beginning, it sounds like it should be the easiest case, but there's conceptual difficulties, mathematical difficulties that come up that aren't present in the infinite square well or other potential energies that go up to infinity, you know, keep getting bigger and bigger as you go farther and farther out. So let's write down the time independent Schrodinger equation. It's the thing we've been doing, but I just set v of x equal to 0, right? You could set v of x equal to any constant, but 0 is sort of the simplest constant you could set it to. So that's saying there's no force, no potential energy for the particle, and therefore it's a free particle. That's an easy differential equation to solve. I'm just going to solve for the second derivative. I get a bunch of constants over on this side, and I say, you know, including a minus sign over on this side, and everything except the minus sign we're going to define to be k squared. In other words, just like we did before, k is defined as root 2me over h bar. And what that means is that the relationship between E and K, solve for E, is that E is equal to h bar squared, K squared over 2m. And that kind of makes sense, right? This is a free particle, you know, from your work with de Broglie, P equals h bar K, right? Should ring a bell. And so this is like P squared over 2m. It's saying its total energy is just its kinetic energy because it's a free particle. There is no potential energy. So that kind of makes sense here. Okay, and we get the nice, simple, so far everything's looking good. We get that harmonic oscillator differential equation, right? We know how to solve that. The solution is linear combinations of cosines and sines, right? Sine of kx or cosine of kx. But we also know from our work at the very beginning of the course, it's just as good to write it as a linear combination of e to the I kx and e to the minus I kx. You can check when you take two derivatives of this with respect to x, you take one derivative, you're going to pull out an ik, right? And get that back. Take another derivative, you get another fact of ik, and I squared is -1. So we get a minus k squared out in front. That's exactly what this is saying. So I could write it as cosines and sines. I decided, we'll see why in just a second, to write it as a linear combination of complex exponentials. Okay, so there's our basic solution. That's for the lowercase psi of x. Now we want to make it time dependent. So here again is the same thing I just wrote up there. Here is my time independent Schrodinger equation solution, one of the possible ones for some particular k. And suppose this is our wave function. How do I make this time dependent? In other words, how do I put time dependence into that one? Suppose we say, in the initial state, I'm in this definite energy eigenstate, right? So at time t equals 0, I'm in this definite energy state because we know a definite k corresponds to a definite E. How do I put in the time dependence? Which one of those is correct? Yeah, I know all of these quantum voting questions, you really have to inspect the details of those. Everything kind of superficially looks the same. So then you got to look at what's different in each one of these.
And even then, we're not always certain, if you know what I mean.
Yes. Is that a joke? There's always a lot of
Yes.
uncertainty in quantum mechanics.
Maybe.
All right, let's see a vote if you got one. There is some uncertainty. I think it's between the B's and the C's. Anybody want to help me verbally tease out the difference between B and C? I think I saw some of both of those. Right. So just for Alvis's sake, let's repeat that. We know the standard operating procedure is if you've got some solution to the time independent Schrodinger equation and you want to make it time dependent, that would mean I'm going to make it into a full separable solution. I multiply by that phi of t, which is always e to the minus I e, well, whatever, if you know, whatever psi this corresponds to, we need to take the corresponding e, t over h bar. So there always should be a minus sign up there, and that actually breaks the symmetry between B and C. One of them had a plus sign in the exponent, but if I plug in E in terms of K right here, notice one factor of h bar here cancels with the denominator. So this simplifies to e to the minus I. One of the h bars cancel. We still have the k squared t over 2m, something like that form. So let's go back and look at this and check out C. You'll see, importantly, both of these linearly independent solutions correspond to the same energy, right? We said both the e to the ikx and the e to the minus ikx, those two linearly independent solutions, correspond to a single energy, right? They both have the same energy, whether, you know, both of those two. So therefore, all I do is multiply each one of them by the corresponding e to the minus I et over h bar, which simplifies down to, so it doesn't really simplify a lot. It looks kind of complicated, but that's what it comes out to when I put in e as a function of k. All right. Okay, so our solutions basically are to the time independent Schrodinger equation looks like this. And if we make them time dependent, you know, if I've got an e to the I minus I times k in this too, right? I've got two factors of k here. So if I factor out an I and a k, both from this and because it was sitting in this part, you'll see Griffiths writes it in this form, which sometimes helps or it sometimes doesn't. But you'll notice that both of these really kind of have the same form. The only difference is whether there's a minus sign or a plus sign up in front of the exponent. Everything else in the exponent is the same. That corresponds to, and notice our definition, I guess I should say, is that k, the whole definition that got us the relationship between e and k, this comes from k is root 2me over h bar. Well, h bar is positive, and the output of the root is going to be positive. So k, at least starting out, is positive, right? We would say we only allow non-negative k's there. But if you're willing to sort of make this simplified a little bit, I always forget, I have to click on this so that this works. If I'm willing to simplify a little bit, rather than having a positive k with a minus sign and a positive k with a plus sign out in front, I could just say, well, let's just write one term and let k go all the way from minus infinity to infinity, rather than having only positive k's and put a plus sign in front of it in one place and a minus sign in front of it in the other place. So we could think of generalizing this solution and the second solution to the right, which were only defined for positive k's, rather summarizing all of those possible solutions by letting k be plus or minus the square root of 2me over h bar. In other words, As E gets bigger, K gets bigger and could be positive or negative. So we would say the allowed values of K, if we're writing it this second way, would be from -infinity to infinity. Okay, each one of those corresponds to a definite E. And when we let K be negative, notice that whatever K I choose, the negative of that K gives the same energy. So both of those, ones with the plus in front of the K or a positive K value or a negative K, correspond to the same energy. Okay, we're going to think about the relationship. So we were talking about the energy of these kinds of states. This is a separable state, or this is one way to write the spatial part of a separable state. That's a solution to the time-independent Schrodinger equation. Now let's think about the momentum of this state, and we're going to find out it's, there's something interesting to say about it. Here are our two solutions before we combine them together. So here I'm still thinking of K as only being positive. So we have a positive K solution that corresponds to having a plus sign, and then one corresponding to a minus sign out in front. And whoever wrote this slide, I didn't do it. They're writing these as psi K and psi minus K, those kinds of solutions where K can go from 0 to infinity, not -infinity to infinity. What happens when the momentum operator acts on those functions? So we have two answers that are being given here, the upper answer and the lower answer. One thing that you should be getting memorized now, even though it's a long way since modern physics, what is the momentum operator? Minus I h bar d dx. If you're talking about a function of t, you need a partial derivative there too. So in this case, since we're letting it apply to a function of t and x, we better put a partial derivative out there. Okay, what happens when we apply that there? Try to tease out the difference between them here. Okay, most of you inside the class are giving signs of being ready to vote. Let's see a vote, and if you got it, flaunt it, as they say. Okay, I'm seeing a bunch of D's so far. Some weren't ready to vote, but I agree. D is the correct answer here, and you just got to mechanically apply minus I h bar d dx. So when I take d dx of either of these functions, of course, I don't have to pay attention to the t stuff. There's no x's in the right-hand factor. But in the left-hand factor, when I take a derivative with respect to x, I'll pull down an ik in the first one and a minus ik in the second one. The minus I will multiply the I in the first one and give 1, right? And then I'll get an extra factor of h bar. So in the very first one, I'll get an h bar k coming out in front. And in the second one, because of the extra minus sign, I'll get a minus h bar k out in front. Okay, and we can think about why this is, I'm not, okay, I actually have a voting question about it. So any questions about D being the correct answer? Do I need to write more about that? When we apply the momentum operator to these two states, the one for positive k's and negative k's, we get, in this formulation, whoever wrote this slide is thinking k is still positive, and we put the sign in by putting an extra minus sign out in front of k. But sometimes we'll think of k could possibly be negative, but not in that slide right there. Okay, now let's think about what that tells us about the expectation value of momentum, and also what the uncertainty or standard deviation in the momentum distribution will be. In particular, you're trying to think of what the uncertainty in momentum would be according to that, given that simple result for those two. Yeah, you might have to write down, if you can't do it in your head, just write down a line or two, see if you can figure out. The answer is 0. This isn't really a voting question, so let's show the board here. Let's see, I need to make sure that I'm writing somewhere that Albus can see. Okay. So we just found out that the momentum operator acting on a psi, plus or minus k, one that has a positive k value or negative k value, is equal to, so we're going to consider k to be positive, that's equal to plus or minus h bar k on psi back again. That's what happens when the momentum operator operates on it. That's what we figured out. Okay, our goal here is to figure out the uncertainty or the standard deviation of the momentum distribution. And the only way we really know how to do that is with expectation values. That's the expectation value of p squared minus the expectation value of p squared. Okay, what's the expectation value of p? Well, let's go into subroutine mode. The expectation value of p is the integral from minus infinity to infinity of psi star p psi dx, right? That's what our standard formalism says. Whenever you have an operator, you want to find its expectation value, sandwich it between psi star and psi and integrate. Okay, what happens when we integrate? Well, p acting on psi gives plus or minus h bar k, right? Times psi back again. The plus or minus h bar of k can come out in front, right? And what's left is the integral of psi star psi from minus infinity to infinity, which is supposed to be 1 if we've normalized our state, right? So this is just plus or minus h bar k. And therefore, this thing right here, when we square it, the plus or minus sign doesn't really matter. This thing right here is h bar squared k squared. Now, can anybody just tell me by thinking through it again in your head what's going to happen for this one? It's the same thing, right? Because I had, in the case where if I want to calculate this, then I have 2 of these. The first one operates on that and gives this, and the second one operates on it and gives it again. So I just end up with the square there. The square of that gets pulled out in front, and we get an h bar squared k squared there. And so those 2 things cancel with the minus sign under the square root, and the uncertainty in the momentum distribution is 0. Okay. What does that mean? If the uncertainty in momentum is 0, the expectation value for a given k value, the expectation value is perfectly well defined, right? If I say k is positive 3 in inverse meters or whatever, the k, SI k units, if it's positive 3, that means I'll be taking the positive sign here, right? Then we just multiply h bar times k, and that would be the expectation value. And we have 0 uncertainty, and that means we're talking about a definite momentum state. Anytime you have 0 uncertainty, but a perfectly sensible expectation value, you're talking about a Dirac delta function, which is a definite state of that particular variable. So we've already known that we found a definite energy state. And we're also finding out now that if you choose a particular K, you get a definite momentum state. Let me back up a little bit here to our solution here. Okay. This corresponds to a particular energy. Both of these summands here have the same energy, because notice whether I take a positive K or a negative K, the energy is h bar squared K squared over 2m. So we're squaring the K. It doesn't matter if we're taking a positive K or a negative K. They don't have the same momentum. In other words, the expectation value of momentum, before I put the square here, the expectation value of momentum depends on the sign of K. So both of these terms here have the same energy. Our whole goal to solve the time-independent Schrodinger equation, it gives us a definite energy state. So both of these terms have to have the same energy. They don't have the same momentum. They have equal and opposite momenta. In other words, when I write it down in this combined state, I could say all the positive Ks correspond to positive momenta. It corresponds classically to a particle moving in the plus x direction. Maybe at 3 meters per second, that would correspond to a particular K. There's another negative K that corresponds to the particle moving in the negative x direction. That would be a minus 3 K and minus 3 in SI units. They both have the same energy, right? If you're moving at with the same momentum in that direction or that direction, you're going to have the same kinetic energy. And in this case, that means the same total energy because the potential energy is 0. So what we're finding is that for the free particle, our states of definite momentum and our states of definite energy are almost the same thing. For every state of definite momenta, well, I guess I should say, if we take a state of definite momentum that corresponds to a definite value of K between minus infinity to infinity, there are 2 values of K that have the same energy. So there's sort of a degeneracy there in that the definite energy state, there are 2 definite momentum states that have the same definite energy. I feel like I'm saying this over and over again, but it's easy to kind of miss that. So not only are we finding definite energy states, but we're finding definite momentum states at the same time. Oh, this was a voting question, but in any case, the answer is 0. Okay. Therefore, when we write psi k in that combined form where k is going between minus infinity to infinity, psi k is a state of definite momentum. And for every k, it's also a state of definite energy. So we've got 2 definite states at once. Okay. Now to some of the interesting parts that makes this different than the harmonic oscillator, for example. Here's a wave function. Okay, I've got an e to the ikx that looks like my definite, my solution to the time-independent Schrodinger equation, and an e to the minus I something times t, so that's putting in the energy part. So this is the generic form for our time-dependent product solution, right? Our separable solution kind of looks like this, but it's written in terms of omega instead of energy, but it has that form. If I take something of that form and I wanted to sketch a graph of the probability density as a function of x, just for any time, you can take time t equals 0. What does it look like? In other words, I want to plot rho of x as a function of x for this particular state. What would I see? If you need to, you can, jot down. Of course, all you need to do at any time, you need to calculate psi star psi, right? That's exactly what rho of x is. What does that simplify to? It looks like it might be kind of a mess, but then you realize it's not. Okay, take another minute. Some of you are ready to vote. Some are still working stuff out. Okay, let's see your vote for that one. I'm seeing it's between the A's and the B's, actually. So let's just work it out. See what it is. Constant in x and t, or it's like a traveling wave. We had the form that was shown was e, this was my psi, as a function of x and t, e to the I kx minus omega t. Psi certainly looks like a traveling wave, right? That's the kind of thing we looked at in chapter 0, but we're concerned with what psi star psi is. What happens when I calculate psi star psi? Yeah, I mean, I get e to the minus I adjunct times e to the plus I adjunct, which cancel itself out. Now, there was also a constant out in front, right? So when I calculate this, I'm just going to get the magnitude of a squared. And that's a constant, no time dependence, no position dependence. So that means at any given time, it looks like this, all the way off to plus infinity. And as time goes on, it doesn't change at all. There's no wiggling to that thing. Of course, this is a stationary state, so there shouldn't be any wiggling, but it's constant in position and time. And that's sort of strange. Why is that problematic? What problem is that going to solve? Cause for us, not solve. It's not normalizable, right? There's an infinite area under the curve. As long as there's a finite area under the curve, we're good. It can't be 0. Can't fix that. Can't be infinity. Can't fix that. So here, we can't have any divergent integrals, and we can't have a 0 integral for psi star psi. So this is a problem that it's constant in x and t. So the way we would phrase this back in terms of when we were talking about states, we did talk about these kinds of functions back in chapter 0, and we said, or maybe it was chapter 1, they're not going to be normalizable, and therefore they're not physically realizable states. Okay, they don't represent possible physical states for a single particle. Now we're going to change that when we have a beam of particles. You know, you might say, oh, I've got a beam of electron. There's an electron here, and then down here, and then down here. They keep going off to infinity. If we think of a beam, maybe we can make sense of this. But for a single electron or a single point particle, it doesn't make any sense. Or at least we can't normalize it, and therefore we can never calculate any probabilities associated with it. So we're going to say it's not a possible physical state. And that means there's no such thing as a free particle with definite energy or definite momentum either. You can't have a particle with definite momentum or definite energy. There's no way to build that state. We can't even know how to think about it in terms of probabilities. But we know also from our work, I guess it was in chapter 1, that we can get really close to that state, as close as we want by, remember when we have a function that's spiraling around in the complex sense, it's a complex exponential function, we can make the area under psi star psi go to something finite by putting a very wide Gaussian curve over it. So we take a curve that hardly changes at all, and then as you get way out, it finally pinches down to 0. And the area under psi star psi is going to be perfectly finite, and we can make the curve as wide as we want, so we can get closer and closer and closer to this state. We just can't produce a state with exactly a definite energy or a definite momentum, but we can get as close as we want. This is saying the same thing for momentum. Definite as goes for energy, in this case for the free particle, there are states of definite energy for the infinite square well. Presumably we can produce one. There's nothing wrong with it, right? Perfectly finite area under psi star psi, but that's not true for the free particle. And similarly, the momentum operator isn't sensitive to the potential energy. So that's saying regardless of your potential energy, there are never states with definite momentum, although we can get as close as we like to a state of definite momentum. All right. Now, the kind of state that a single particle can be in can be written as an infinite linear combination of these states. That just because you can't have a particle in one of these states, It might be that if you take a linear combination of these states, you could produce a state that has the integral under psi star psi be perfectly finite. And that's exactly what we're going to do. Okay, so just like back in the case of the infinite square well or the harmonic oscillator, we said, more generally at time t0, I could write my most general, boundary condition at time t equals 0 to be a linear combination of all the definite energy states. Here, our definite energy states look like this, at least, at time 0, right? I haven't put in the time dependence there, right? There's one for each real number k, right? K doesn't have to be discrete. Up here, the energies were discrete. But down here, the energies are continuous. We said the energies are h bar squared k squared over 2m, where k is anything between minus infinity and infinity. So k is a continuum. Since k is a continuum, unlike n, I can't just sum over n like I did here. If k is continuous, I'm going to need to integrate over k. So we just do the analogous thing with integrals. So here is, for example, if I want to say, let's make a perfectly reasonable function that, it doesn't necessarily have a definite energy and it doesn't have a definite momentum, but it's a linear combination of these states. These states have problems by themselves, but let's take each one of those, put a coefficient in front of it, and the coefficient can change. The thing that indexes what energy we're in is k here. So just like the coefficient can change with n up in this case, the coefficient here can change with k, because k is what tells us what state we're multiplying by. And then add up that linear combination. We're summing up coefficients times those states. And when we sum over continuous things, that's an integral. The 1 over root 2 pi, don't worry about it. It's just a conventional kind of thing we put out in front. But, if you could think of it as being part of the phi of k, right? It's just part of a big coefficient that's going out in front of this, right? So the phi of k's are like our CNs, and Griffiths calls it phi of k. That's pretty common notation in quantum mechanics. Okay, if that's what it is at time t equals 0, and somehow I figured out what phi of k is, it's the same way we figured out what the CNs are. We'll talk about how to do that. Then I could put in the time dependence here. I can change that t equals 0 to a t by doing what? It's what I'm showing in red here. I know the red's hard to see in the room. I can put in the t by taking each term, and when I say a term, I mean when you're integrating, it's like you're adding a bunch of stuff up. So this is one term right there. I multiply that term. Oh, this is a typo. It shouldn't be an en. It should be an e corresponding to k. Each e corresponds to a k. And just like n told us which definite energy state we were in back in the infinite square well, k, which is a continuum, tells us which definite energy state we're in for the free particle. So that should actually be an ek. I just changed this right before class and I made a mistake. And then so here I just substituted ek as a function of k. So it gives you that mess we looked at earlier. Okay, and that's, so our goal is, if you want to have your wave function, you have a free particle, and you want to predict what its shape is as a function of time, and you know what its shape looks like at time t equals 0. And we will do an example. I don't know that we'll get to it today. We'll see. Suppose my psi as a function of x and 0 for a free particle, it does something sensible. I like things that, go to 0 like that, and they're constant because they make your integrals easy to do a lot of the times. If that's the case, then we want to know, as time goes on, how does this thing wiggle and jiggle? Well, what I need to do is write this as a linear combination phi of k e to the ikx. I need to write it as a linear combination of these definite energy states, and they're also definite momentum states. This is true for any k. I need to sum over all k's, and by convention, we usually put a 1 over root 2 pi out in front. You can think of the 1 over root 2 pi as being part of the phi of k, so it's just part of those coefficients, but by convention, people factor that out there. And then, if I want to put in the time dependence, well, I'm not going to write it down here, but you just plunk that thing in there. E as a function of k, e to the minus I ek t over h bar. Okay. So unfortunately, we know that this e to the ikx function has a definite wavelength, right? K is 2 pi over lambda. So if you tell me a k, I'll tell you the lambda. We can think of it as having a definite wavelength as it swirls around in the complex sense. That means that when we've taken a linear combination of those, we no longer have a definite range of wavelengths, and therefore we don't any longer have a definite range. We don't have a definite value of momentum. And since each one of these corresponds to a definite energy and we're taking a linear combination, we don't have a definite energy anymore. But so, if I take this state as my initial state, most likely that's going to be an infinite linear combination of definite energy states. And I have a variety of different energies I might get if I measure the total energy of that, which in this case would just be the potential energy. Okay, so the one missing ingredient now is if we want to write psi of x0 in the way I'm just had up on the board and I have right here, if I want to write this, so then later on I can put in the time dependence, the question is, how do I find those phi of k's, those coefficients? And the answer is, well, it's sort of the same way we did before, except it's harder to do the derivation now. There's some wishful thinking in the derivation. But there's a theorem you can prove if you're in analysis called the Fourier-Plancherel theorem, which tells us something very similar to what we found out before in the discrete case, right? What did we find out in this discrete case? We found out that if I want to write psi at time t equals 0 as a linear combination of the psi n's, the CNs were an integral of psi of x0 times psi n star. And you're seeing a very similar formula here. If I want to write a function of x, this is like my psi of x0. I wrote it in a generic form here. So this is like our psi of x0, and here's our definite energy state right there. If we want to write it as a linear combination of those, here's a formula that tells you how to calculate f of k, or our phi of k in our notation, right? What you do is you need another factor of 1 over root 2 pi out in front, and you multiply, just like I was multiplying by psi star here. Here our psi is inherently complex, e to the ikx. So when we stick our psi of x0 next to psi star, that star really matters. We need the minus sign in the exponent there. Okay, but compare again to what we found out before. If this is psi of x0 being written as a linear combination, our Cn looks like it almost has the same form. You integrate with respect to x, psi of x0, there it is, times psi n star. In this case, it's a psi k star because it's indexed by a continuous variable, not a discrete one. Okay? Now, there are some restrictions, and all of this is in the details of the proof of the Fourier-Plancherel theorem, which I certainly don't know. But if you're studying analysis, this is something that you could prove. It's not easy to prove just using the tools that we have at hand here. In order for it to apply, there are some suppositions that you have to, conditions that have to be met by that function f of x. In other words, you can't do this for any old function f of x. F of x has to satisfy the following property, or our psi of x0 has to satisfy this property. The integral of the magnitude squared of f of x dx has to exist. And when I say exist, that means it has to be finite. Being infinite, we're not going to call existing. So it can't be a divergent integral of any kind, and it can't just simply go to infinity or anything. It's got to be a finite number. But that's okay for us because we're talking about for us, this is psi of x0, and we're hoping it's a normalizable state, right? We're hoping we've already normalized it. Maybe there's area 1 under the curve. So we're talking about states that definitely should satisfy the conditions for the Fourier-Plancherel theorem to apply. Okay, so here's a little notation or terminology for this. The Fourier-Plancherel theorem tells us if you've got a function f of x and you want to write it as a linear combination of e the ikx's, here's how to find the coefficients you need. The coefficients, which we're calling phi of k, here in this version it's called capital F of k, it's called the Fourier transform of the function. Okay, so this is my function that I started with as a function of x. This function of k that we're getting, which is the coefficients over here, is called the Fourier transform of f of x. And similarly, f of x, if somebody gives you a phi of k, that's defined this way, you might say, well, what's the corresponding f of x I would need to put in there to make this true? It's called the inverse Fourier transform of that function. So these two functions are Fourier transforms or inverse Fourier transforms of each other. Okay, so translating into our notation, this is saying define that phi of k. Here's the formula. You just like before for the CNs, you take psi of x and 0 and multiply it by the complex conjugate of the definite energy state. And by convention, we put this 1 over root 2 pi out in front. And you might say, well, look, this function might have problems. It just keeps winding around as it goes off to infinity. But hopefully this function closes down to 0 fast enough that this integral actually exists, right? That's what we're hoping. It's got it. That's what the conditions on psi of x and 0 or that f of x involve. It's got to have a finite area under the curve. Okay, so that's how we get our psi of x and 0. And then we can put in the time dependence as time goes on. Okay. Now let's think about the relationship between this boundary condition, the initial condition for the wave function, and those coefficients. Does this contain more or less or the same information as the original boundary condition? In other words, if I tell you phi of k, is that just as good as knowing psi of x at time t equals 0? Or if I tell you psi of x, is that just as good as knowing phi of k? Or does one contain more information than the other? Okay, we're running a little bit short on time. I see a 3, see a couple 3s out there. Some people are still flipping it. The correct answer here is 3, and you can see that at a glance when you look at the formulae we just wrote down, right? Here's the formula for the relationship between psi of x0 and phi of k. And you can see if somebody gives you phi of k, if they tell me an explicit formula for phi of k right there, I can reconstruct psi of x and 0 by doing that integral. So phi of k contains just as much information as psi of x and 0, right? Similarly, if someone gives me psi of x and 0, I can reconstruct phi of k by the phi of k formula. So they're completely equivalent. It's the same way with the CNs, right? You might say, hey, I really like knowing the initial condition. But if somebody gives me those CNs, it's just as good of enough information as psi of x and 0. Because if you give me these CNs, I can perform this sum and figure out what psi of x and 0 is. And if you give me psi of x and 0, I can compute the CNs. So they're equivalent, but different representations of the same state. Okay, so sometimes there's a lot of notation here, but we're almost to the point where we're going to start doing practice problems, but it doesn't look like today. It'll be Monday. Because of this, phi of k, we think of as a different way to represent the state that we're in at a particular time. So I might say, I could tell you what state that we're in at time t equals 0 by drawing phi of x and 0 as a function of x. But just as equivalently, I could give you phi of k. And phi, because p equals h bar k, this is just as good as giving something as a function of momentum. If I know what it is as a function of k and p is h bar k, then I know what it is as a function of momentum. People talk about this as the momentum representation of the state. And we're going to shift our thinking more and more as time goes on in that we've been kind of really attached to functions of x up to now in the course. But the idea is knowing what things are as a function of x is just as good as knowing what they are as a function of k. Or if you go back to the c's over here, it's just as good as knowing the function at time t equals 0 is just as good as knowing these cn's right there. And so I can think of cn's as a new way to represent the same state. It is a kind of a wave function. I can give a wave function as a function of x at time t equals 0, or I could give that same information, the Fourier transform, as a function of k. And we'll call that the momentum representation. Conventionally, we write it as a function of p if we really want to call it the momentum representation. And we might call this the wave number representation. But it's just as good as this. And we're going to start switching back and forth between these and thinking, who cares? Why do we always have to live in x land? We could live in k land for a while and specify some initial conditions as a function of k at time t equals 0, right? And then predict. And then if you really want to know it as a function of x, we'll have a way to compute that using, if somebody gives you phi of k, I can always get the information as a function of x by performing this operator. So they really are completely equivalent. Okay. Oh, it's a bad time for a worksheet right now. Let me just set up the worksheet. I'm not even going to hand it out right now. I'll hand it out on Monday. The idea is I have a state very much like this. Our state looks like this. Between minus a and a on the x-axis, here's what psi of x and 0 looks like. At time t equals 0, this is what our wave function looks like. 0, 0, 0, 0. Then it goes up to 1, or we've got to figure out what this normalization constant a is going to be, right? And then it goes down to 0 again. So the first thing, of course, you have to do is normalize. Not surprising, it's going to be 1 over root 2a, right? Or when you went from 0 to a, it was 1 over root a that went out in front. So here we're going to have a 1 over root 2a. But the goal is now to be able to write psi of x and t. To write psi of x and t, my first work I have to do is to write this as an infinite linear combination, coefficients phi of k, figure out what those coefficients are, of these kinds of functions, sum over all that index k that we have to do. Of course, I get those phi of k's from the Fourier-Plancherel theorem, which says they can be calculated this way. Integral from minus infinity to infinity psi of x and 0 times e to the minus ikx. And there we're integrating with respect to x. So that, if I can carry this out, that gives me these coefficients. And then once I've got those coefficients explicitly, I can put in the time dependence by, I didn't leave myself enough room here, by putting in e to the minus I ek t over h bar. And ek is nothing but h bar squared k squared over 2m. That's what the energy is that corresponds to k. P squared over 2m. It's a free particle, so it only has kinetic energy. All right, we'll do that on Monday, and the interest is in what happens with the actual solution here. It's kind of an interesting solution. Questions? When's our next homework due? Today, Monday? We've got, I guess it's Monday. The 1 through 4, okay. And then the next ones are due sometime early next week, which is 5 through 9. Those are on the infinite square well. And it is important that we tighten that up and try to get them done by Monday at the end of the day at the latest, because we have an exam on Wednesday, and my intention is to have the cutoff for the exam be the harmonic oscillator stuff, not this free particle stuff. We're going to continue working on it through the exam probably. So if you got your 1 through 4, I take it back. If you got your 1 through 4, keep them and turn them in with 5 through 8, just so you can keep them and sort of look at them over the weekend. I will try to have a very quick turnaround for 1 through, not 5 through 8, I think it's 5 through 9. Try to have a quick turnaround for those at the beginning of next week. But try to finish those over the weekend, the first 5, and then we can talk about any questions